right when I start recording. Obviously, we get an announcement. Okay, if you've got to go for your pictures, by all means, that's what you've got to do. Don't bump that cart. Oh, you can go at the back door, too. Oh, don't bump the cart. Nice. All right, so last day after the quiz, we talked fairly quickly about atomic theory. And I talked a little bit about some historical importance of the atomic theory. I'm not worried about dates. Again, I just tell you those stories and I tell you those dates to kind of give you a timeline on what's happening here. So today we want to talk about atomic notation and isotopes. So again, we're now talking about the nucleus. Now, why do we want to talk about the nucleus? Well, to a chemist, the nucleus is very important. The nucleus contains the protons, and the proton, the number of protons, identifies the substance, right? So let's talk about how we indicate that number of protons. So first, we're going to talk about atomic notation, and the first thing I'm going to define is the atomic number, all right? And that atomic number is given the symbol Z. I'm not exactly sure about the origin of that symbol Z. It's been used for years. In university, I've taken courses on what is called quantum mechanics. It's a very high-level explanation of the way atoms behave, and whenever we need to insert the atomic number into the equations, Z is what we use. So, you know, I tell you that the term or that the symbol is Z, and you might think, why do we give it such a symbol so we can just write it down? In higher level chemistry and physics, when you do calculations involving atoms, you will use the symbol Z to represent the atomic number. It represents the number of protons present in the nucleus for a given element. And so therefore, it identifies the element. You can see that in the last bullet. I talked briefly a couple of lessons ago how Mr. Vandenbroek changed the periodic table so that it was ordered in atomic number. And I did a brief explanation on how the atomic number was empirically determined, experimentally determined, using X-rays and firing them off of atoms and having the X-rays bounce off and catching the X-rays and doing some math. This is our theoretical definition of atomic number, number of protons. That's what makes it theoretical, because we can't actually see the protons in the nucleus. If we're talking about a neutral atom, which we will when we get rolling, it's also the same as the number of electrons in the atom. Okay. The mass number. I do have lots of, again, historical references and stories that go along with this. I'll backtrack once we've defined this, and I'll talk a little bit about the history of how scientists came around to discover some of this stuff. The mass number is given the symbol A, which seems kind of silly because none of those words start with A, but atomic number does. So it's completely backwards. It's the sum of the number of protons and neutrons present in the nucleus of the atom. Remember last day we finished off, we did that table comparing the charges and the masses of the atoms, or sorry, of the subatomic particles. And the protons and the neutrons had a mass of 1 each, and the electrons were very small, 1/2000th. Which means when we are looking at an atom, we only look at the masses of the protons and neutrons because the masses of the electrons are very minuscule compared to it. So we can ignore them. You might say, how could we ignore such a thing? When an atom loses an electron to become an ion, because the electron is so small, its mass is so small, the mass of the overall thing doesn't change. That'd be like saying, to you, step on a scale and then go have a haircut and then come back and step on the scale again. The scale will read essentially the same because the mass of that hair that's been removed, that little bit, is so small, it doesn't affect your overall mass, right? So you don't have to, every time you get a haircut, you don't have to call the, Department of Transportation and have your, driver's license updated because really your mass is essentially the same. So our mass number is the protons plus the neutrons. We don't worry about the electrons. This allows us to get then the number of neutrons, take the mass number, subtract the atomic number, all right? The mass number is always the big number, and the atomic number, which is the protons, is always the small number. Always take the big number, subtract the small number, you get the number of protons. So let's now take a look at this, and I do want you to write all of this down, even, this cut and paste that I did from a textbook. So I'll write this with you on the board. This is representing a fictitious element X. So the way we write an atomic notation is we put the element symbol, and then at the top we put the atomic number, and at the bottom we put the, at the top we put the mass number, at the bottom we put the atomic number. If you want to kind of summarize this without writing it all out, you could just put here number of protons, number sign P plus. I guess I can write on the smartboard for those who are maybe watching. So here, an easier way to put it here is just to put number of protons. All right? This top one up here is number of protons plus the number of neutrons. Right? That's what it represents. So we have our atomic number at the bottom, and we have our mass number at the top. Here's a couple of examples. Carbon. And you can see here that I have two different forms of carbon as my example. I have carbon that has a mass number of 12 and carbon that has a mass number of 14. So two different types of atoms that come from the same element. And this type of thing is true for many elements. Alternative ways to represent the elements, just writing the symbol, dash, and then the mass number, C12. Another way of writing it, the name, carbon-12, carbon 12. The other version of the atom would be called C14 or carbon 14. In the standard atomic notation, there's actually some redundant information. It means that there's information presented twice that we don't really need. Chemists are really good at naming things because there's so many things that have to be named. We're usually pretty good at getting rid of redundant information because it doesn't make sense to write things twice. But in this notation, there are two things that represent the same thing. Which two pieces of information in this standard notation tell us the same thing? So in this standard notation right here, we have three pieces of information, and two of these pieces of information tell us the same thing. Which two pieces of information tell us the same thing in that notation? Which two things and that notation tell us the same thing. They would lead us to the same endpoint. All right, Abby, what do you think you got? Yeah, correct, the 6 and the C. Why is that? That's correct. And the 6 protons tells us it's carbon, and the carbon tells us it's carbon. So the 6 and the C tell us the same thing. So when we write something like carbon 12, we've gotten rid of the redundant information, but if I know my periodic table, I can always go from the carbon to the 6, and I can always get that atomic number of 6. So the lower ones are actually a little more streamlined. The reason we have these lower ones is because they're easier to type. It's a pain to type superscripts and subscripts, right? If you're not good with the computer, that's a real pain to do. So just writing C-12 is an easier way. So if you come across a news story, maybe using maybe about a nuclear something, maybe they're talking about burying the nuclear waste up in Bruce. You know, that's the big news thing now. They want to bury it very deep in the rock. If they're talking about a particular atom, you'll see them write something like U-235, which will represent a uranium atom with a mass of 235. Because they can type that easier, they would not write the standard notation, because many people wouldn't know what it means. All right? Let's do a quick little practice problem, and then I'll talk a little bit about how you can have atoms that are the same yet different, like our carbon atoms. They're kind of special. They're the same, they're both carbon, yet they're different. So let's now do some calculating here and determine, or let's just practice writing some atomic notation here. And actually, I should have done a couple of example problems back on the previous page. I'll do those in the end. I'll create one more example problem. So we have a potassium atom that contains 19 protons and 20 neutrons. Determine the atomic number and the mass number of the potassium atom. So I'm hoping you're writing away, getting caught up, but I'm going to just kind of start the process. So the atomic number, Z, and the mass number, A. What's the atomic number going to be if our potassium atom contains 19 protons and 20 neutrons? The atomic number going to be? What do you got? 19. How'd you get that? Yeah, protons is the atomic number. It's correct. The number of protons is the atomic number. We also have a periodic table right out here in front of us. And if we take a look at potassium, we'll see that the atomic number is 19. So the K tells us that, and the 19 does. Atomic number of 19. What's the mass number going to be? Or tell me what I need to do to find the mass number. What do I have to do to find the mass number here? Yep. Add them together. So I'm going to need 19 plus 20. I'd hope we wouldn't need a calculator for that. What do we get? 39. So we have a mass number of 39. All right? Okay. Write the symbol for this in 3 different ways. Somebody tell me one way in which we can represent this particular atom using the 3 different methods that I had on the previous page. What's one way of writing this particular atom? 3 different ways. You're going to look at your previous note, the previous slide that you just wrote. You'll notice I had 3 different ways of writing that carbon atom. Transfer that to this potassium atom. Yep. K39. Awesome. K-39. Correct. How else could we represent that? Garrett, what do you think? Potassium 39. Excellent. Oh, I got to check potassium. I'm going to spell it wrong. Potassium 39. Now the hard one. How am I going to represent that? Tell me what symbols to write and what and where to write it. Jillian? Okay. So at the top is 39, and at the bottom it's 19. Excellent. Okay? Let me do one more example for you, and I'm going to just write this off to the side. You can call this like number 2 if you wanted to call this number 1. And here I'm going to ask you to determine the number of protons, number of neutrons, and number of electrons, assuming it's a neutral atom, in, and I might as well use that atom I just talked about a moment ago, U-235. All right? So if I've got U-235, I want you to tell me the number of protons, the number of neutrons, and the number of electrons. Okay? And guess what? The thing we always start with is the protons, because it's the easiest. All you got to do is track it down. You got to do some looking for a number. How many protons are in a U-235? And some of you are getting out your periodic tables. That's awesome. I have a nice large one right here for those of us who are not visually challenged. Number of protons in a U-235. Yep. 92, correct. How did you get that? Yeah, you just looked at uranium, you looked for the atomic number. Correct. 92 protons in a uranium-235. 92 of them. Awesome. Number of neutrons. You can either tell me what the number is or tell me what mathematical thing I'll have to do in order to get that number, and then your friends can like activate their calculator and solve it for you. What do I have to calculate? What do I have to put in there to get the number of neutrons? I don't have names figured out, so I can't pick on people yet, except those that I know. That's always fun. Jillian, what do you got? Sorry, say that again. Yes. So what are those numbers? Just tell me what the numbers are.
For the instructions, students from last name of H, I, or J, please go to Gen C for your pictures.
What is the mass number? I want you to tell me what that number is. Yes, it is. That's correct. 235 is the mass number. That's the total mass. 235 minus 92. So how many neutrons in this thing? Somebody get their calculator out or their phone. By the way, when we do real calculations, which we will be doing some later today, you'll want your calculator out. You're not going to want to run through your phone. And I'm not going to let you use a phone during a test. So you got to have one. Sorry? 143? 143 neutrons. We like that, checking the math, because I can't do that in my head. 143 is good? If this is a neutral atom, how many electrons are there in this thing? If this is a neutral atom, how many electrons are in this particular atom? Jillian? 92. It's the same as the protons. They got to cancel each other out. 92 electrons. That's the type of calculations you would have done in grade 10, I think. Very much of a review. Okay? All right. Excellent. So let's move on. Now let's talk about what these atoms are that have the same identity but different masses. And the term we use is isotope. And that's a term you might have heard in the past. I don't know. I'm thinking you can let them in that back door if they're coming in. Actually, probably prefer that. But anyway, it doesn't matter. That's fine. This is a term you may have encountered in grade 10, depending on who your teacher was. Yeah, not a big deal. Okay. So, isotopes are atoms of an element which have the same number of protons and electrons, if they're neutral, but different numbers of neutrons in the nucleus. And this definition is the blank definition out of our two definitions that we know, right? The other definition is atoms of the same element with the same atomic number, but different mass numbers. And that's the blank definition. So, same number of protons, different number of neutrons. Or, another way of looking at it is the same atomic number, but different mass numbers. We saw that with the carbon. They both have 6, same atomic number, but one had 12 as the mass number, and one had 14 as the mass number. So now, to get us to think again, because that's my job, to make you think. Which definition is this, and which definition is this? We know what I'm talking about, my 2 possible definitions that we define everything with, empirical and theoretical. Which one is which? Which is the empirical definition, which is the theoretical definition? What do you think? Empirical definition or theoretical definition? Empirical, based on experimental evidence. They did something in the lab, they looked at it. Theoretical, based on an idea. What do you think? Correct. Why is that? The protons and the neutrons are just a theory. We can't actually have a look inside the nucleus and see that. So you're right. It's based on the idea that there are these protons and neutrons. So this is theoretical. Making the other one empirical. And that's because, again, in the laboratory, we can do experiments, we can make elements, we can weigh them, we can do things to determine what the mass is. We could use X-rays and that fancy technique that I talked about, which we wouldn't, but somebody did, and they did a lab on it, so we can get the atomic number empirically. So this is empirical. Excellent. All right? So it turns out that atoms of an element are not exactly the same. Let me tell you a little story about where this came from. It goes back to radioactivity. And I should maybe teach radioactivity first. I should maybe flip it around, because tomorrow I'm going to talk about radioactivity, all right? But I think you have an idea on what radioactivity is. It's dangerous. It comes from stuff. It's usually associated with nuclear something, like a nuclear power plant or a nuclear bomb. And these things are all true. Now, radioactivity was discovered about mid-1800s by the name of a guy by the name of Becquerel, and it doesn't matter who this guy is. But Madame Curie, and I've already mentioned this, she's the rock star of radioactivity. She took this concept and this idea that certain elements were giving off some kind of radiation, and she started to do chemistry with those elements. And the first element that she worked with was uranium. Now, we're going to learn tomorrow that when radioactive uranium does its thing and is radioactive, that it turns into another element. It turns into thorium. Now, thorium was already known to exist. Chemists had found thorium, so that wasn't very exciting. But when thorium breaks down, it breaks down into, where are we? It breaks down into radium. Now, radium was not known to exist, but Madame Curie, when she was studying the uranium, found that chemicals were being formed that were made of thorium, and then chemicals were being formed that were made of something they had never found before, a new element. A new element had been discovered through this radioactivity. She called it radium because it radiated. It produced the first radiation that they were really looking at. She continued to do her work, and the next thing that she discovered was polonium. Her home country was Poland, so she named it polonium in honor of her home country, all right? Now, as they started to do more and more experiments, Madame Curie not only discovered polonium, she didn't call it polonium right away, but she simply gave it a position, but she found that a different version of the same atom was being formed. So they were having the same chemical properties, but their masses were different, just like our definitions. They had the same atomic number, but different mass numbers. At first, chemists thought they had discovered new elements. They thought that they had discovered some crazy exotic new element that had the same atomic number but a different mass number. So what chemists envisioned was now a three-dimensional periodic table. Not only did they have a position for their atomic number, but you could pile them up on top of each other with the lighter ones on the bottom and the heavier ones on the top. So different masses then would stick out in a 3D periodic table. Chemists realized in the end that it didn't matter what the mass was, that they all behaved the same way. So a polonium with a mass of 209 behaved the same way as a polonium with a mass of 208 that had one neutron difference. All right? So they discovered that it didn't matter what the masses were, that even though there were these different massed elements, they all behaved the same way. All right? So they needed a way to describe these elements that had the same number of protons, the same elements, but different masses. The term isotope is made up of two pieces. The first part, iso, and you'll encounter that many times in your science careers, means the same. So iso means the same. Tope comes from the same word as like a topographical map. You remember using those in geography? Did you look at the topographical maps, find where the elevation is and all that type of good stuff, right? Tope comes from topographical map. It simply means place. So isotope means the same place. And what that translates into is when they started to discover that there were elements of different masses, they realized that they really were sitting in the same place on the periodic table. So isotopes means that they're atoms with the same atomic number or number of protons. The mass might be different, but they all exist in the same place on the periodic table, and hence they're called isotopes. All right? That information is not needed ever on a test, but I learn better when I know where words come from in order to help me, understand them. So when we have two elements that have the same number of protons but a different number of neutrons and a different mass, they're called isotopes because they sit at the same place on the periodic table. Excellent. All right, here's some examples of some isotopes of hydrogen. I do want you to write this down. Don't write down the pictures with the protons and neutrons. Just write down the symbols and write the names and write down the subatomic particles that are in them. So please just write the, this bottom portion of this little note here. So this is just an example. Hydrogen has 3 isotopes. Now notice what they've done here. They've added even another notation. What's missing in this notation? What's the piece of information that's missing in that notation? Which piece of information is missing in this way in which we're writing this? It looks kind of like the standard notation, but something's missing. Gee, how do you find that answer? Maybe you could go up and look at the standard notation and see which of the things is missing. Crazy. What's missing in there? Come on, Garrett, picking on you now. Go back to the atomic notation. Go to that thing where I said C or X or whatever it is. You see it?
Yeah.
All right. What's the top number mean? All right. Oh, the top number is the mass number, so we're saying this has a mass of 1, this has a mass of 2, this has a mass of 3. What's the bottom number? Oh, so what's missing? Isn't it amazing when you go back, you can actually find the answers? Isn't that awesome? The atomic number is missing. But remember, we just said that was redundant information. If I know it's H, I know the atomic number is 1. So they're just, saving the typing, so we don't have to type it. All right. We have 3 types of hydrogen. Hydrogen 1, this is the most common form of hydrogen. So when you drink a glass of water, all of those H2 on the H2O is predominantly made up of just one proton in the nucleus. That's it. There's a small amount of that water. Some of the H's will be made up of H2. It'll have a proton and a neutron, a very small amount. In a regular natural water, which you'd find maybe in a lake that is far away from a nuclear power plant, actually, even the water by a nuclear power plant, you wouldn't have it. You would find a little bit of this and a little bit of this. This is man-made. This is made in a nuclear reactor. This is radioactive, and this is dangerous, the tritium. So in nuclear reactors, where that water is manufactured, and it's not manufactured on purpose, it's kind of like a side reaction, they have to gather all that up and keep it stored and safe so that it doesn't get out into the environment. All right? The isotopes of hydrogen are so important that we give them special names. We could call this hydrogen 1, hydrogen 2, and hydrogen 3, but because it's so important and we use it so much, we call H2 deuterium, du-2, and H3 tritium 3, all right, for the mass numbers. All right? Very important isotopes. All right, we're moving along nicely. So you can write that last little thing about isotopes, and you'll notice I'm to the point where I'm going to give you some work to do, but you're going to find I'm quite mean. I'm not going to let you work. That'll be homework. I'm now going to talk about the next topic that goes along with this. Since isotopes of an element contain the same number of protons and electrons, they have the same chemical properties. It means chemically they behave the same way. An H1, you can make water out of regular hydrogen, regular H2O. You can make water out of deuterium. It would be a little heavier because it's got extra protons in it. It's actually called heavy water. You can actually create water that has all deuterium atoms. It's called heavy water. It literally is heavier. But it would have the same chemical properties, right? It would behave the same way. It would taste like water. But isotopes of elements vary considerable in their physical properties. So they're heavier. Uranium-235. U-235 is a very rare isotope of uranium. Uranium's predominant isotope is uranium-238. So if you have a chunk of uranium, most of the uranium is 238, and very little bit of it is 235. It turns out that if you want to run a nuclear reactor or build a nuclear bomb, you need uranium-235. This is the only isotope of uranium that can be used in a nuclear reactor or to create a nuclear bomb. If you've taken some history and you've learned a little bit about World War II, you've probably learned a little bit about how the United States versus the Germans were desperately trying to create a nuclear bomb. And you may have heard something called the Manhattan Project. Now, the Manhattan Project was the Americans' plan to produce the first nuclear bomb. The only problem was they needed lots of this. And the only way that you could get lots of that was to separate the two masses. The way they were separating the isotopes back then was with something called a centrifuge. A centrifuge is a device that you use that you put maybe liquids or mixtures in, and it spins it around very fast. It's used in biology quite a bit to separate blood into its various components. Have you ever seen or heard of a centrifuge? They spin around like crazy. Yes, centrifuge, all right? If you've ever been on one of those rides that spin you around and bring you up on the side, that's kind of like a human centrifuge. I don't know if you're separating humans with that. The United States built massive facilities in the desert that contained millions of centrifuges. And their job was to get that centrifuge to spin. The heavy uranium would be pushed to the outside, and the lighter uranium would be near the top. And then they'd have to separate that very carefully. It took them many years to get enough to build one bomb because you need a certain amount. But they won the race. They won that particular race, and they created the first nuclear bombs before the Germans did. And the rest is history, right? And the Germans lost, and they bombed Japan a couple times, and that type of stuff. But that's they used the physical properties of the uranium-235 to separate them out because they couldn't use chemistry. If you did a chemical reaction, they'd both react exactly the same way. You couldn't separate them by chemistry, by maybe reacting them with something else. You couldn't do it. You had to use their mass to separate it. Okay, average isotope and atomic mass sheet. If we go to the day's work page, all right, and I haven't got that opened up yet, let me open that up. And again, this is where you guys are finding, your thing. This is terrible. I'm struggling here. Escape. Discard. So this is where you're going for this type of thing. 3U. Right? So this is not on Google Classroom. This is just a practice sheet. So you go to the day's work page. You go to today's date, the 15th, and there you can see the handout, Isotopes question sheet. And do you want to print that and do it on the page, or do you want to just put it on, or just put it on a separate piece of paper? That's up to you. Okay? But that's the homework I'm talking about on the day's work page. That's up to you to get, find, print off. Okay? So 1 and 2 deals with what we just talked about, and 3, 4, and 5, I'm going to talk about that right now. All right? So you can now do 1 and 2, and I'm going to continue on and talk about average atomic mass. Okay? All right. So again, that's your responsibility either to print or to just look at and do it maybe under your note as homework, right? However you want to do that. It's up to you. If you go to the course content page, you will find the solutions page in section 1, and the answers to that sheet are in the solutions page. So now we want to talk about units, how we measure these atomic masses, and we also want to talk about the mass number that we find on the periodic table, because it's a little different than what we've been talking about. So the first part of this second section of the lesson is about units and how we measure these protons and neutrons. I'm just going to see, does it go? No, I got to back up. So, a little bit of history again. How did chemists measure elements? Well, chemists measured elements' masses way back when, 200 years ago, by comparing them to each other. They knew that if they produced some hydrogen, that they always produced a very little bit of hydrogen. And if they produced some carbon, it was always so many times more than the hydrogen. So in the beginning, chemists said, well, let's divide all of our numbers by the mass of hydrogen. That will make hydrogen become 1, and everything else will be related to it. Okay? But then chemists did more work, and they found that as they got better at measuring, decimal places came in. They didn't have nice whole numbers, 1, 2, 3, 4, 5. They had decimals, so they thought there was a mistake in their particular calculation. What they didn't realize is that there were isotopes, different types of each one. So they thought they had a mistake. And somebody doing a lot of math determined if we... I want a baseball bat. Yeah, out the back door would be better. So someone did a bunch of math and realized that if they took the mass of oxygen to be exactly 16, they could get rid of the decimals. And it made life nice and easy. So instead of letting hydrogen be exactly 1, they said, let's make oxygen be exactly 16. We'll divide everything off by 16 and then multiply it and get the numbers. The decimals disappeared. Awesome. Then they discovered isotopes. And they realized there has to be decimals in there. And they said, what do we do? Well, chemists decided, let's use something that's really important to like life, like carbon, and let's let carbon be exactly 12. So we're going to force a carbon-12 isotope, a carbon-12, to be exactly 12 units. So they defined the unit as that. So if you take the mass of a carbon-12 and you divide it by 12, you get what is called the unified atomic mass unit, U. And it is 1/12 of the mass of a carbon atom. And that's our standard. That's how we weigh protons and neutrons. A proton is 1 U, and a neutron is 1 U. And what is that compared to? A carbon-12 atom divided by 12, 1. Okay? Now, just to mess things up, physicists still like using oxygen as 16. So if you have a physicist's periodic table and they're doing nuclear physics, your numbers are a little different. What a mess. Some nuclear physicists still work on this 16 oxygen table. They're crazy. Don't mind those nuclear physicists. We're going to use carbon-12 as our standard. Along with the advancements of science, we now know exactly how much this 1U is. It turns out it's 1.66 times 10 to the minus 24 grams. It's a tiny little number. But we're talking about a tiny little particle. So it doesn't have a lot of grams. So when we talk about atoms and protons and neutrons, it doesn't make sense to talk about grams. They're too small. So we talk in terms of U, atomic mass units. 1 proton is 1/12 of a carbon atom. It's 1 U. Okay? So when we write our units to mass numbers, the unit is U. All right? Okay. The next thing that brings us to is what we call the average atomic mass. I'm going to let you write that, and then I'll do my talking. Already got it written down? Nice. You're to the examples. You have no idea what to do yet? That's okay. That's good. Using your device for good? Nice work. Why don't you show Abby how to do that sometime? So this brings us then back to our periodic table. What have we learned today? Well, if I give you the example of carbon, I've told you that there's something called carbon-12 and there's carbon-14. There's actually even different versions of carbon beyond these. So some of the carbons have a mass of 12 and some of the carbons have a mass of 14. But they all behave the same chemically, so we don't care what their mass is. What we want to know is, if I have a hunk of carbon, like in a piece of charcoal, what's the average of these masses going to be? Now, you might say, well, that's easy, Mr. Sanders. The average of 12 and 14 is 13. That's the average mass. And that's true. That's the average of the two numbers, but it wouldn't be a weighted average. If I take a look at the actual weighted average atomic mass, which is what's found on the periodic table, I have 12.011. So it's really close to 12. Let me explain to you what a weighted average is. Let's use our ages as the example. So we are in grade 11, which means we should be soon driving. Fun stuff, fun stuff. Saw on Facebook, Allison went for a drive the other day. My brother is weird. So anyway, you guys know what I'm talking about. Anyway, how many of you are 16 years of age? 16. Raise your hand. Oh, actually, let me just put here 16 years, and then I'm going to count you. Raise your hand, 16 years of age, nice and high. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 of us are 16 years of age. There are 14 of us. Awesome. How many are 17? 17-year-olds. Excellent. So, oh, yeah, we got one there. That's all right. It's okay. You know, you got a good reason to be here. Don't feel bad. So we got a 17-year-old. 17 years old, 1. And 15 years old. You guys haven't got there yet. That's exciting. Nice and high. 15. 1, 2, 3, 4, 5, 6, 7. 7 of you. So 15 years age, there are 7 of you. All right. Excellent. Now, if I were to ask you, what's the average age of the class? What's the average age of the class? What would you say? What's the average age of the class? You'd say 16. I don't know who said that because I'm not hearing very well. 16. Now be careful. That would be the average of the numbers. If I take 15, 16, and 17, the average of the numbers would be 16. But that's not necessarily the average age. That's not the weighted average, because I didn't take into account the number of 15-year-olds, the number of 16-year-olds, and the number of 17-year-olds. Let's figure out the fraction. What percentage of the class is 15-year-olds? Well, I know the class has like 32, but of the people that are here, what have I got? 14, and plus that is what, 21, 22? Only 22 of us in this room at this point in time. Did I miss any like 18-year-olds? No, 14-year-olds, prodigies? No, 13-year-olds, geniuses? All right, let's just assume 22. That means 7 out of 22 are 15-year-olds. Make sense? And 14 out of 22 are 15-year-olds, and 1 out of 22 are 16-year-olds. I now need some calculator assistance. Could we divide that and turn that into a percentage? Could somebody tell me what the decimal is? Let's get the calculators out, people. Come on, we need calculators. If you got them, get them out. Yep. This is 31.81, 31.8%. Nice. Second one. Sorry. 63.6, 63.6. Nice. And the last one. Yep. 4.5. 4.5. How can we check if we're correct? Add them up. What should be true? Should be 100. We got it right? We're looking good? 30, 90. Yeah, we're getting really close. That's awesome. So how do we then determine the average age? Well, I need to take my 15 years of age, and I need to see what percentage of that total average is worth the 15-year-olds. So what I do is I multiply it by the percentage. 31.8 divided by 100 to turn it back into a decimal. What chunk of the average age is worth due to the 15-year-olds? Someone do that calculation. In other words, I've taken 15 times 31.8%. So you got that number? Don't be afraid. Fire them up. Yep. 4.77. That means 4.77 of our average age is due to the weight of the number of 15-year-olds. I'm going to do the same for 16-year-olds. 63.6 divided by 100 to turn it back into a decimal. What portion of the average age is due to the 15-year-olds? Yep, 10.17. They're the most, so it has the greatest effect on the weighted average. 10.17 and 17 times 4.5 divided by 100. And what value of the average is due to our 17-year-old? That's okay. We needed a 17. If it's just 15 and 16, it wouldn't be fun. 0.76. 0.776. Add them up, and we will have what is called the weighted average that takes into account the amount of each of the age. The more there is of that age, the greater effect it has on the average. So what is our average? Did we add them up? 15.7? 15.7. Why is the weighted average less than just taking the average of the numbers? Why is the weighted average less than 16? Why is that weighted average? That's the average age, by the way, in the class, 17, 15.7. Why is the weighted average, this number, less than just the average of the numbers? The answer is right there in front of you. Why is that the case? Any ideas? All right, let me guide your thinking. What would have to be true about the 15 and the 17-year-olds to get an calculation at the end to be exactly 16? What would have to be true? And what would have to be true about the amount of 15-year-olds and the amount of 17-year-olds? You're right. There'd have to be less and more. What would have to be true about the number of 15-year-olds compared to the number of 17-year-olds? They'd have to be exactly the same. So they applied the same weight on the opposite side of the 16. Notice I have more 15-year-olds. That brings down the average below just averaging the numbers. That results in an average age being a little bit less. Let's go back and look at carbon. Let's assume that carbon is made up of only 12 and 14. If I see that the average weight of carbon is 12.011, what does that tell me about the relative amounts of the 12 versus 14? In other words, if I were counting carbon atoms, how many 12s would there be and how many 14s would there be? And I'm not looking for an actual number. I'm just looking for a description. Yep. There'd be a lot more 12s than 14s because our average is right on 12. That means there's got to be tons more 12 than 14s. There can only be a few 14s for each 12. If we look at hydrogen, and we remember the fact that hydrogen's made up of naturally 1 and 2, and the weighted average is 1.00794, what does that tell us about the relative amounts of the 1s versus 2s in hydrogen? My average is 1.00 something something. What does that tell us about the amounts of H1 versus H2? Not looking for numbers, just looking for a description. What's there the most of? What's there the most of? Yeah, because we're really close to 1. There's got to be tons of H1 and very few of H2. Let's do some examples. A couple of examples. Now, chemists have a very good way of determining the percentage of each of the types. They have a device that's called a mass spectrometer. A mass spectrometer takes a mixture of substances that have different masses, and it spreads them out. It spreads it out by mass. Kind of like a centrifuge, but it's not a centrifuge. It uses magnetic effects, like the way I bent that beam the other day with the magnet. It uses the exact same effect, but I'm not going to get into detail. So what chemists can do, actually J.J. Thomson, you know our electron guy from yesterday, the electron guy, going to remind you, think back to yesterday. We talked about Democritus, then Dalton, then Thomson. Mr. Thompson invented the mass spectrometer. He's a very smart guy. Anyway, in a mass spectrometer, you inject some material, like some chlorine atoms. You let it go through the mass spectrometer. It does this thing, it turns a corner, it illuminates this thing, and through some computerized equipment. After it comes through the mass spectrometer, you can know for certain that 75.53% of the atoms have a mass of 35, and 24.47% of the mass of the atoms have a mass of 37. Just like I did when I counted you guys, except a computer does it. That means 75% are 35 and 24% are 37. The average mass. I'm going to first do the calculation with you, and then I'll write an equation for it. But we've already done this. Just like age, I am interested in what part of the mass is due to the 35. So you can imagine them like age. They're 35-year-olds. Chlorine, no, it's not. It's 35U. The mass of 35 then needs to be multiplied by its percentage. 75.53 divided by 100 to turn it into a decimal. That tells us the chunk of the mass that's due to the 35s. I then want to add to that, I did it up and down on the board, but we can just put it beside it, the chunk of the mass that's due to the 37. 37 times 24.47 divided by 100. When you do this little calculation, you'll get the chunk of the mass that's due to the 35s. When you do the second calculation, you'll get the chunk of the mass that's due to the 37s. And I would take these as individual numbers, if you could please calculate them for me. Megan, you done? Oh, wow, she's done. I was just joking. I didn't think anybody could possibly be done. What do you got? 26.44 plus 9.05, and when you put them together, 35.49, and we should always have units on our answers, and the answers are U, atomic mass units. For those of us who like equations, average mass. This is the mass number, A, right? Remember we call that the mass number? And I'm going to call that the mass number of element A. So I put a subscript, little a, to represent that it's the first one, times the percentage abundance. I'm just going to put a bun. The percentage abundance tells us how much there is of each one. So it's the percentage abundance of A. See, I put a little subscript A divided by 100. So what did I do? I took the mass of A times the percentage abundance, how much of, what percentage of it is it, divided by 100, plus the atomic mass of B. Yay, that's fun. I like the trend here. B times the percentage abundance of B divided by 100. And I'm going to put here a plus, and then I'm going to put dot, 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 3 dots, dot, dot, dot. Because sometimes some isotopes have 3 of them, or 4 of them, or 5 of them. There's all kinds of different isotopes. So however many you have. Okay, one more example. Boom. Oh no, that was the only example I'm going to do. Oh, I thought I had 2. That's awesome. So that brings us to the end of our discussion of isotopes. That sheet I just described you has the last questions, which deal with that. And then there's also some textbook questions. All right? let me show you one more thing when you're done writing that stuff down. I want to show you where I supply you with the solutions to either textbook questions or worksheets. So notice today, our sheet is not being marked, and therefore it's not on Google Classroom. The sheet is just a practice sheet. It's found on the day's work page of the website. Now I'm going to, let him in. I'm going to bring this back up, but I just want to show you one thing on the website, all right? So if you take a look, pay attention to me. Don't mind him. Don't mind that guy coming in the door. Okay, so if you take a look at the website, there's the sheet. Back to the website, the day's work page. Again, if you go to course content, this is where I've hidden things like solutions. If you go to Part 1, Unit 1, Part 1, you'll notice here, it says here, solutions. Here it says textbook solutions. So you know how sometimes they've got the answers to the numbers right there in the column? That's awesome. If it's a longer written out question that they don't have the answers right there, you can find the textbook solutions by looking at what page number it is. You can see I've got it broken down to the page numbers, all right, where to find it. I'm going to go back one. Notice also here, oh, go back for me. Oh, no, I don't have to go back. Close. If I go to course content again, and I go again to Part 1, I shouldn't have closed that. Part 1. And I go to solutions. And notice right here, Isotopes question sheet. Open that up. It has the answers to that big page. It also has the answers at the end here for all of the masses. So you can find the answers to all of your sheets in solutions. All right? Okay? All right, I'm going to go back so that people can finish writing that down. And as I'm doing that, I'm going to shut off. Oops, I'm sorry. I'm blocking the way. I'm going to shut off my recording.